In this given example, triangle ABC is isosceles, meaning it has two congruent sides, a pair of two congruent sides, right? And then AE is congruent to AF, the sides of the largest triangle, respectively. So we provide the given statement, we justify it as given. The next statement immediately follows that AB is congruent to AC. And the reason for that is simply, right, this isosceles triangle is that isosceles triangle has at least, when I say at least, yeah, equilateral is considered technically isosceles as well, but usually when we're talking about isosceles, we're talking about exact two, but at least two is still correct to say. At least two congruent sides. You might ask now, but how do you know that AB is equal to AC and not AB equal to BC, for example? Notice that if BC, if you use your eyes and you make, notice that it looks like it's shorter than AB, so to make it longer, BC would be somewhere here, right? C would be somewhere there, okay? But look what happens. If we put C here, that means we would create a line segment from E to here. Now remember, you have to assume all of these are line segments, straight lines, in other words, right? They're not bent in any way. BD is on the same line as DF, right? Same line BF. So these line segments, they would be different, right? Because the D point would be somewhere there as a result, right? So if you make a line segment EC, it would be there. So notice what happens. ED has become longer and DF has become shorter. But look what you have to do. You have to prove that DE is congruent to DF. So when you have to prove it, you will assume it is true, because otherwise how are you going to prove it? Right? So DE is congruent to DF, but in this picture, no way, it's not. And the reason why it's not is because we moved the C point downstairs. We could move it upstairs, it will still kill this statement that we have to prove. There's no way that DE would be equal to DF, right? So the C point must be where it is, right? So that EC would be congruent to BF, because otherwise how are we going to prove that ED is going to be congruent to DF, right? So if we put the C back to where it was, we make AC congruent to AB. There's no way that AB is congruent to BC or AC is congruent to BC. This BC is not part of the isosceles triangle being the way it is, right? So AB and AC are congruent. Okay, so great. So now the next statement immediately is going to be that triangle AEF is isosceles. Now, how do I know that it is isosceles as well? Well, notice that it's given that AE is congruent to AF, right? So isosceles triangle, as it was, has at least two congruent sides, as was already declared, right? So this is technically the definition, right? So we write this reason for statement 3 as the definition of an isosceles triangle. Right? At least two congruent sides. Great, this fits the description. AE is congruent to AF. So that also tells you that these two are similar, right? The smallest one and the biggest one are similar. Okay, but we're not technically going to use that similarity. We're rather going to do something else. So let's now point out the fact that AB is equal to AC, right? Since AB was congruent to AC, then the lengths of these two are equal, right? So AB is equal to AC. Now AE is equal to AF, right? Because of that given statement, AE is equal to AF. The length of AE is equal to the length of AF. And the reason for that, of course, is the definition of congruent line segments, right? Because we're talking about congruent line segments AE and AF and AB and AC, as we already pointed out in statement 2. Now the next statement is going to be, of course, we're going to use the addition postulate. Notice that AB plus BE is equal to AE. Let's picture that. AB plus BE is equal to AB, right? Using the addition postulate. And similarly, this side is going to be AC plus CF is equal to AF, right? So the reason for that is simple, right? This is the segment addition postulate. Now the next part, we have to use substitution. Okay, so notice that AB plus BE is equal to AF, and similarly AB plus CF is equal to AF. Now how do I know that this is true? Which substitution did I use for this? I used the substitution on line 4. Notice that AB was equal to AC, right? And AE was equal to AF. So basically I substituted the AE with AF, and then I substituted AC here, as you can see, with AB based on this first equation, right? So this is simply the substitution property of equality. Substitution property of equality. Okay, so now the next step is going to be this. Notice that AB plus BE minus AB is going to be equal to AF minus AB. I'm just simply subtracting AB from on both sides of the first equation. I'm going to do the same thing on the second equation. I'm going to subtract AB. So AB minus AB plus CF is equal to AF minus AB. AF minus AB. And this is going to be the subtraction property. Subtraction property of equality. Okay, and where am I going for this? Notice that I'm trying to isolate BE and CF in both of these equations respectively. And why do I need it? Notice that we're heading closer and closer to ED and DF, the thing that we're trying to prove. So we're going to work with these two triangles, BEF and CFE, in order to derive proper relationships and prove them congruent, so that we can work on individual parts ED and DF. And you'll see how I'm going to get there. Right? So now we're going to isolate BE. So BE, as a result, is equal to AF minus AB, AF minus AB, and then here CF is going to be set respectively to AF minus AB, AF minus AB. And notice this does something really beautiful. And this is substitution, right? Because we substituted AB minus AB is 0. 0 plus BE is BE, right? So this is a substitution step that we've carried. So this is substitution property of equality. So now notice something beautiful. AF minus AB is on both sides, so that means that these two can be set equal, right? So BE can be set equal to CF, right? That's what we wanted. And again, this is the substitution, and I'm going to put this in quotation marks because that's the same as the previous step, substitution property of equality. Now the next step is to notice that since the lengths of BE and CF are the same, that means that these two are congruent, right? These two are congruent. And this is actually the reason for this is segments of equal length are congruent. Another reason would be basically definition of congruent segments if you wanted. That would be another reason that you could include. That would work. Okay, so now the next step is to see that EF, so notice that we're trying to prove these two triangles congruent, BEF and CFE. We already showed that one of their sides is congruent, right? So BE and CF are congruent. And notice that they both share, these two triangles, CFE and BEF, share common side EF. So first we're going to show that EF is congruent to itself. EF is congruent to itself, and the reason for that is the reflexive property of congruence. Okay, so this is the reflexive property of congruence. Okay, so now we already know. So we already showed that this side is shared, and they also have the same sides as well. Now notice that we have one more before we show congruence. Notice that these two angles are congruent. So BEF, and these are angles of the largest triangle that we started with, right? When we showed AE and AF, right? So AEF angle is congruent to AFE. Okay, so these two angles are congruent. So so AEF is congruent to AFE. And by the way, you could say it as well as BEF is congruent to CFE, right? Because the first letter doesn't matter, the angle does not change. It's still that angle that you're talking about, right? So you could do it either way. So now notice that the reason for this is that angles with congruent opposite sides are congruent. Okay, are congruent. I probably should rewrite this. Just don't have enough space. Are congruent. Okay. So now the next step is to already show that these two triangles BEF are congruent. BEF is congruent to triangle CFE. Okay, and how do we know that they're congruent? We already showed side angle side, right? These two sides are congruent as we showed here, BE and CF. These angles are congruent as we showed AEF and AFE, right? And then the side is shared. So side, angle, side, right? So that means we can say side, angle, side, postulate of congruence. Okay, so now we know that their individual parts will be congruent as well, because BFE, notice that this are individual parts, right? BFE, right? So individual parts of these triangles will be congruent as well, right? Because we already showed that these two triangles are congruent, right? So we can say that angle BFE is congruent to triangle CEF. Okay, and the reason for that is that corresponding parts of congruent triangles are congruent. CPCTC, corresponding part, in this case corresponding parts are these angles of these two triangles that we showed were congruent in step 13. So now the last thing is pretty obvious, right? Because if these two angles are congruent, and we're talking about the base angles of triangle EDF, right? These are the base angle of this triangle here, EDF. So that means if these base angles are congruent, the opposite sides to these congruent base angles must be congruent. And guess what? These are the opposite sides that we're talking about that we need to prove, right? So DE is congruent to DF. And the simple reason for that is opposite sides of congruent angles are congruent. Okay, so this is it. I hope it was helpful. See you in the next video.